So we have physics PhD qualifying exam practice problem number 5 in classical mechanics. So let's begin. A particle moves in the potential v of x equals a times the square root of x, with a is greater than 0. For part A, describe the phase space trajectory for fixed energy E. So this is an action angle variables problem. So for part A here, we're going to let the mass be m. The Hamiltonian here, h of x comma p equals p squared over 2m plus a times absolute value of x equals e, where a is greater than 0. The phase space trajectory from energy conservation, p squared over 2m equals e. H equals p squared over 2m plus a times absolute value of x equals e. And our p would be plus or minus square root of 2m times this quantity e minus a times square root of x. And sorry about that. Should be closed parentheses there. Let me put that in here. Whoops, that should be in there. So turning point occurs when p equals 0 and e equals a times absolute value of x equals 0. So x equals plus or minus e over a. And that would also, our x max is going to equal a over e over a. And our phase space trajectory is the closed curve. So p equals plus or minus the square root of 2m times quantity e minus a square root of x, close parentheses here. And that's for negative e over a is less than or equal to x is less than or equal to e over a. So that's part A. Part B, we want to compute the action variable here for j equals 1 over 2 pi, that closed integral of p dx, or integral over one complete cycle in phase space. So moving along to part B. So part B here, the action variable here is j over 1 over 2 pi closed integral of p dx, and by symmetry the closed integral p dx, that equals 4 times this integral from 0 to e over a square root of 2m quantity e minus ax dx. What we're going to do here is let u equal e minus ax, du equals negative a dx. So j equals, and we're just we're going to skip over some of the computation. We arrive at j equals 2 times square root of 2m over pi a, integrated from 0 to e, u to the 1/2 du. And when we perform our operations, j is 2 times square root of 2m over pi a times 2/3 e to the 3/2. And j would equal 4 times the square root of 2m over 3 pi a times e to the 3/2. So that's our j value. Now moving along to part C, express the energy as a function of j. Okay, so whoops, sorry about that, for part C here. So solving for E to make this a function of j, we have j, and just performing the operations, algebra, e of j comes out to quantity 3 pi a j over 4 times the square root of 2m, and that is raised to the 2/3 power. So that is part C. Part D, determine the oscillation frequency. And we could do this, there's two ways we'll show doing this. For the first way, while the angular frequency is omega equals this derivative e with respect to j, e of j equals cj to the 2/3. Omega is 2/3 cj to the negative 1/3. J equals this quantity here, 4 times square root of 2m over 3 pi a times e to the 3 halves. And our derivative of j respect to e is 2 times square root of 2m over pi a times e to the 1 half. So omega equals derivative of e with respect to j. And this here, this dj de -1, that equals pi a over square root of 2 times the square root of 2me. Okay, think about where that comes from. So omega is going to be pi a over square root of 2. I'm sorry, pi a over 2 times the square root of 2me. Okay, so here, that's the first way we could calculate omega, and let's do the second way here for this. Let's see, we find the period directly. Let's see if this will hold. Okay, so find the period directly for x is greater than 0. E is 1/2 mv squared plus ax. Solving for v is the square root of 2 times the quantity e minus ax over m. Then dt equals dx over v equals square root of m over 2 dx over a square root of e minus ax. So a quarter period is going to be t over 4 equals the square root of m over 2 times that integral 0 to e over a dx over the square root of e minus ax. And if we use u equals e minus ax, t over 4 equals the square root of m over 2 times 1 over a integrated, the integral times the integral here from 0 to e, u to the -1/2 du. Sorry, that's a -1/2. And here, t over 4 equals square root of m over 2 times 1 over a times 2e to the 1/2, which is the square root of 2me over a. So t equals 4 times the square root of 2me over a. So our omega is going to be 2 pi over t, which is going to be pi a over 2 times the square root of 2me. So that's another way to get our omega. Now for part E, just going back here, for part E, we want to determine whether the frequency depends on the amplitude. So for part E, and let me just switch this here for part E. So for part E, here's what we could do. Amplitude is A equals E over A. We're going to substitute here. E equals a lowercase a times capital A. Omega equals pi a over 2 times the square root of 2ma equals pi over 2 times the square root of a over 2m capital A. So what we could say here is omega is proportional to a to the -1/2. So the frequency is going to decrease as the amplitude increases. Okay, and for part F, we want to compare this oscillator with the harmonic oscillator. So compared with a harmonic oscillator, okay, whose force is given as that -kx, and whose frequency is given as a square root of k over m, independent of amplitude. Well, here we have v of x equals a times the square root, a times the absolute value of x. So f equals the negative derivative v with respect to x equals that -a sine function, and except at x equals 0, where the potential has a cusp. So the restoring force has constant magnitude rather than growing with displacement. And what we could say here is this oscillator is anharmonic, and its frequency depends on the amplitude. So this is just a quick overview of this Ph.D. Qualifying exam in physics, classical mechanics, practice problem number 5. Thank you for watching, and have a great day.